Let's continue from the chapter 3. It is about the solution of differential equations of dynamic systems. Yes, as you know, all physical systems are represented with the differential equations. So it is so important to solve these equations. We consider the systems that are modeled by ordinary differential equations. Okay, ordinary differential equations. What is the outcomes for us? If you successful completion of this chapter, we can learn convert linear time invariant ordinary differential equations into Laplace domain. Laplace domain. Find the transfer function, poles, and zeros of differential equations represented in Laplace domain again. Find the response of linear time invariant differential equations using inverse Laplace transform. Understand the behavior of first and prototype second order differential equations. And we will not learn in this lecture state space model. Okay. In engineering, a wide range of systems are modeled mathematically by differential equations, as you know. These equations generally involve derivatives or integrals of the dependent variables with respect to the independent variable, usually time for us. For instance, RLC circuit here we did at the last lecture. For example, these systems has a second order differential equation, as you see here, or the first order but one integral term here. It means actually second order again. As the same way for the spring mass damper system, we have second order differential equation as given here. What is the standard prototype second order system? It can be given again in 3.4. Yes, linear ordinary differential equation. Maybe we can use writing for this lecture mostly. Okay, in general, the differential equation of an nth order system can be written as d to the power of n yt over d2 over t to the power of n plus a minus 1 d to the power of n minus yt divided by d t to the power of n minus 1 and blah blah until a1 dyt over dt plus a0 yt, and then it is equal to b subscript by m d to the power of m ut and dt to the power of m and plus again m minus 1 d to the power of m minus 1 dut over dt to the power of m minus 1 plus blah blah until again b subscript by 1 dut divided by dt plus b0 ut. For this system, we know this yt is the output of the system. So a0, a1 and blah blah until a n minus 1. It is the coefficient, real constant coefficients for the output. Okay, real constant coefficient for output. Okay, as the same way we can say ut is the input of the system and b0, b1 and blah blah until pm. They are again real constant coefficients for inputs. Okay, but in here we know that we accept that t greater than t0 and t0 always 0 for the control. It is mean that it is causal or physical system. Yes, what about the first order linear ordinary differential equations? It is the general form for the first order dyt over dt plus a0 yt is equal to ft. Ft is the input for this system. What about the second order? Second order system, we can say d to power of 2 yt and d t to power of t plus a1 dyt over dt plus a0 yt is equal to ft. Yes, this is the second order and the first one is the first order. In here the first equation is the nth order differential equations. Okay, let's continue now. What about the nonlinear differential equations? We saw at the last lecture for the nonlinear system this formula. And we said before the nonlinearity term is sine theta. So we accept theta 0 is 0 and small changing o theta, we can accept sine theta approximately equal to the theta. So the linear equation or linearized equation for this system rho over L theta is equal to 0. What about the Laplace? Yes, Laplace transform. Why we need to Laplace transform? You need a special and also homogeneous solving, if you remember. Laplace reduce a linear differential equation to an algebraic equation. Okay, so we need to use Laplace transformation. It's a technique, one of the mathematical tools used to solve linear ordinary differential equations. It is important. It is used for only linear systems. Okay, Laplace transform defined for only linear systems, not nonlinear. You cannot use Laplace transform to solve nonlinear equations. So this approach is very popular in the study of control systems because the homogeneous and particular components in the solution of the differential equation are obtained in one operation. The Laplace transform converts differential equations into simple to manipulate algebraic form. What about the definition of the Laplace transform? Let's assume that we have a function in time domain ft. The Laplace, and we have to know this function is 0 to infinity range. The modulo of this function should be finite value. Okay, if this equivalent is not satisfied, so we cannot use Laplace transform again. Sigma value is real, we know this. So the Laplace transform can be defined as, for this function, 0 to infinity ft e to power of minus st dt. Okay, you can use this formula to convert your equation to the Laplace domain. Fs means Laplace transform OFT. Also, it can be represented as Fs also can be represented as Laplace symbol and Ft as here. We know this S is the Laplace operator, and we know this it is a complex variable. Okay, complex variable. Actually, it means sigma plus g omega, and sigma is a real part and omega is the imaginary part of this operator. Okay, what is g means? G is mathematically a square root of the minus 1. But here, as you see in this equation, it is only defined until 0 to infinity. It means we don't consider the before, okay, before the 0. It means on the control theory, this system is causal or physically realizable, okay, one-sided Laplace transform. For the Laplace transform, we consider the 0 to infinity time range. It means one-sided transform. Okay, let's do an example now. We have a function ft is equal to ut, which is defined 0 for t less than 0 and 1 for t greater than and equal 0. Let's get the fs value. Get fs or Laplace transform of ft. How can we do it now? Fs is equal to 0 to infinity ust ut, or maybe we used u, yes, ut times with 8 power of minus st dt. So for this equation we know 1 over s 8 power of minus st, which is range 0 to infinity. Now we can get 1 over s finally. This is the unit function, unit step function. Okay, ut is called as unit step function. Another example for the Laplace transform. Ft is equal to 8 power of minus 80, which defined t greater than 0. And we know this a is real constant, not a function of t. So the Laplace transform of this function can be written fs is equal to 0 to infinity 8 power of minus 80 times 8 power of minus st dt. And then you can get for this equation 8 power of minus s plus a t over by the s plus a, which range 0 to infinity again. So you will get 1 over s plus a. This is the Laplace transform of the ft. Important theorems for Laplace. The first one is the multiplication by a constant, which is represented as kft. ft is constant, okay? How can we convert this into the Laplace domain? K times fs. And the second one is the sum and difference, Laplace transform of the f1 t minus or plus f2 t. And in Laplace domain we can say f1s minus plus f2s. That's our algebraic specification of the Laplace transform. What about the differentiation? The Laplace transform or the dft over dt is s fs minus f0. f0 means initial conditions. So if you have nth order differential equation as like that, you can find s to the power of n fs minus s to the power of n minus 1 f0 minus s to the power of, maybe it is convenient to write here, s to the power of n minus 2 f0 superscript with 1. It means the differentiate one time and 0 for this condition, and you will get you will continue as like that. And the lastly you can say fk 0 means, as I said before, d to the power of k ft dt to the power of k, which is t is 0. K means in here kth order derivative of the f. What about the integral? For the integration, the Laplace transform of the integration f tau d tau is equal to fs divided by s. So the generalization of the integral specification can be given tn 0, tn minus 1, 0, and blah blah. And the last one will be t1, 0, ft d tau dt1, dt2, and blah blah, dt n minus 1. Okay, how can we convert it to the Laplace domain? Fs over s to the power of n. 5. For the shift in time, the Laplace transform, if f function is shifted in time, us t minus t can be given e to the power of ts fs. This is the shifted ratio or shifted time. us t over t is defined 0 for t less than t and 1 for t greater than and equal t. The other specification, initial value theorem. initial value theorem. In this theorem, we know this limit t goes to infinity ft is equal to limit s goes to 0 as fs. Sorry, for the initial t goes to 0 and s goes to infinity. What about the final value theorem? For the final value theorem, limit t approaches to infinity, now ft is equal to limit s approaches to 0 as fs. Initial value theorem gives the initial value of any function, and final value theorem gives the final value of any function. Yes, the other specification, complex shifting. Complex shifting, if you want to get 8 power of minus or plus at ft, Laplace of this function, it's mean in the Laplace domain s minus plus a. Okay, real convolution, it's not important. Convolution we will not we don't need to see, because you will see in the signal processing lecture. The new term for the control, transfer function. Transfer function, in classical control, transfer functions are used to represent input-output relations. Okay, in the control theory, transfer functions gives us to input-output relation. For example, the nth order differential equation given in here, maybe we don't need to write again, nth order differential equation. For example, these equations, if you convert these equations into the Laplace domain, you can get the input-output relation. So how can we do it? Let's do it. For these equations, we will convert this equation to the Laplace domain. How can we do it? The nth order differential equations, as you know, the Laplace term will be s to the power of n. If you assume zero initial conditions, we don't need to write f 0, 0 and blah blah. Okay, assume that for the zero initial conditions we will do a conversion plus blah blah a1 s plus a0 parenthesis by ys equal to bm s to the power of m bm minus 1 s to the power of m minus 1 and blah 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 b1s b0 parenthesis by input, it's mean us. So you will get input output relations as ys divided by us is equal to bm sm bm minus 1 sm minus 1 plus b1s and b0 divided by s to the power of n an minus 1 sn minus 1 blah blah a1s plus a0. Okay, this is the input output relation for this system, and we call it as transfer function. The transfer function of a linear system of differential equations is the ratio of the Laplace transform of the output to the Laplace transform of the input. as you see here, the Laplace transform of the output divided by Laplace transform of the input. Okay. All initial conditions of the system are set to 0 for the transfer functions. All initial conditions set to 0. Okay, the transfer function is independent of the input of the system. How can we say this? As you see here, if we say this is a transfer function of the input, is there any input value? No. So we can say transfer function is independent of the input of the system. Okay, the other term is important for us, characteristic equation. Characteristic equation of a linear system is defined as the equation obtained by setting the denominator polynomial of the transfer function to 0. For example, in this formula, if denominator of this transfer function is set to 0, so this is the characteristic equation for us. Okay, so for the above equation, we can say s to power of n plus s to power of n minus, we have to consider coefficient blah blah a1s plus a0, as I gave before, yes, is equal to 0. This is the characteristic equation. So we can say all of the characteristic equation of the system is obtained from the denominator. Yes, the other term is analytic function. If a function of gs is called as analytic function, where, of course, S domain, all its derivatives exist in the region. All its derivatives in the region. For example, gs is equal to 1 over s times s plus 1. What can we say about this function? This function gs is analytic functions where, except for at this point, s is 0 and s is 1. Besides these poles, we can say gs is analytic function. For example, the other example, gs is equal to s plus 2. What can we say about this? This function is analytic for every point in the finite S-plane. Okay. Poles of a function. A pole, also known as a singularity, plays a very important role in the classic control theory. The poles of a transfer function are the points which gives infinity for the transfer function. For example, if you have this kind of transfer function 10 times s plus 2 divided by s plus 1, s plus 3 to the power of 2. The poise for this function, the poise is set to characteristic equation to 0. S is 0, S is minus 1, and also S is minus 3 are the poles OGS. Okay, as you see here, we have 2 poles for the minus 3. So we can say at minus 3 we have second order pole. Okay, second order pole. But the other of them, minus 1 and 0, is the first order poles. Okay, how can we represent poles in the graphic? In the control theory, we used graphics as like that. For the poles, we used this symbol. As you know, it is the origin, it means 0, and this is real part, or we can say sigma, and this is imaginary plane, we can say g omega. The other poles is here, minus 1. At minus 1 we have another poles, and minus 3 we have 2 poles. What about the zeros for the function, for this function? Zeros do setting to 0 the transfer function. So for this function we can say S is minus 2 is 0 for this function. Zeros becomes 0 to the transfer function, and minus 2. We used a circle for the represent 0. Okay, sorry about that. Minus 2, not a pole, it is 0, can be represented as circle as see here. Okay, I have to say you this, for any transfer function, the number of the poles are equal to the number of the zeros. How? For example, GS is equal to 10 times S plus 2 and S minus 1, plus S plus 3 to power of 2. For this transfer function, we saw poles 0, minus 1, minus 3, and minus 3. So we can say the number of poles 4. 1, 2, 3, 4. What about the 0? For the same transfer function, 0, minus 2, and what? Where is the other 0 for this function? If you do a limit for this function, limit s approaches to infinity gs, you will see that limit s approaches to infinity 10 over s cubed is equal to 0. So we can say at the infinity we have 3 zeros for this function. Infinity, infinity, infinity. Okay, so the number of the zeros are 4, we can say. Let's continue now. Complex, conjugate, poles and zeros. Remember the second order prototype system. Gs is equal to omega n square divided by s square plus 2 zeta or xi omega ns plus omega n square. Okay, if your zeta or xi is less than 1, it is mean that your poles will be minus sigma plus and minus g omega n 1 eksi xi square. So we say this sigma is the real constant, sigma real part, and it is equal to C omega n. It is the damping ratio, and omega n is the natural frequency we saw before. If you want to learn exactly what is mean, you will understand next chapter. Okay, we can show this Poise S-plane sigma and g omega as like that. Okay, it's R, and at this point S1 is minus sigma plus g omega. Maybe we can say easily omega means omega n times 1 minus c square, and S2 is minus sigma minus g omega. Okay, we can represent this Poise in the S-plane as like that. According to this shape, we can say minus sigma is equal to R times sine phi. Where is phi? Angle from 0 to this vector. And what about the others? Omega, we can say R times cosine phi. And the same way we can say this angle is minus phi. So R will be for us sigma square and omega square and square root all of this. And phi is arctangent omega divided by minus sigma. Let's continue from final value theorem. Limit t approaches to infinity ft is equal to limit s approaches to 0 as fs. Okay, let's do an example now. Example fs, for example, 5 divided by s square plus s plus 2. What is the final value of this expression? Let's get it. Limit s approaches to 0 as fs is equal to now 5 divided by 2, as you see here. This is the final value of this function. For applying the final value, the Laplace transform of ft is fs, and if sfs is analytic, okay, we can apply this theorem. So s times fs should be analytic to apply final value theorem. Okay, let's repeat again. S times fs should be analytic to apply final value theorem. It's important. Also, we have to know this. The final value theorem is not valid if s times fs contains any pole whose real part is 0 or positive. Okay, s times fs, if s times fs contains any pole whose real part is 0 or positive, we cannot apply. Let's continue from inverse Laplace transform. What does mean inverse Laplace? Inverse Laplace mean we select a domain to use from time to S domain. Okay, if you want to go again time domain, we have to do inverse Laplace transform. Ft is the inverse Laplace of the Fs, and we can represent this as like that. How can we do it in mathematically? Ft is equal to 1 over 2 pi j integral c minus j infinity c plus j infinity fs e to power of st ds. Okay. To convert Laplace into the time domain, we will use this formula. C is the real constant, so that greater than the real parts of the all singularities of Fs. Okay. Greater than real parts of all the singularities. To convert your function from time domain to Laplace domain, you can use the Laplace transform table. Also, you can use the inverse Laplace conversion table to convert your function from Laplace to time domain. But we have to know some analytic approximation to convert your function. For example, partial fraction expansion. If we do this, we can convert S domain to T domain easily. The general transfer function can be given Qs divided by Ps, polynomial of Q and polynomial of P. And we know this Ps and Qs are the polynomials of S. It is assumed that the order of Ps in S is greater than that of Qs. The order of Ps is greater than Qs. Okay. So the polynomial Ps may be written as Ps is equal to S to power of n, an minus 1, Sn minus 1, and a1 as a0. Okay, we know this a0, a1, an minus 1 is the real coefficients. Okay, let's see now partial fraction expansion. How can we do it? How can we simplify the GS to convert T domain easily? If GS has simple poles, simple poles mean all poles are not equal to each other. Okay, so we can write this function as like that: Qs divided by S plus S1, S plus S2, and blah blah, S plus Sn. Okay, we can apply partial fraction expansion to this equation, and we will get GS is equal to KS1 divided by S plus S1, KS2 S plus S2, and KSN S plus Sn. As you see here, I is 1, 2, to n, subscript according to the Poise. And so KSE is coefficients with respect to the SE pole. Okay. So how can we get KSE coefficient? K subscript by SE is equal to S plus SE times gs, where s is equal to minus se. Okay, we can get kse as like that. For the, as I said before, simple poise. All poise are different from each other. Let's do an example now. gs is equal to 5s plus 3 divided by s plus 1, s plus 2, and s plus 3. As you see here, poise are minus 1, different from minus 2, and different from minus 3. So we can say this is simple. This function has simple poise. Okay, so we can apply as like that, k minus 1 s plus 1 plus k minus 2 s plus 2, k minus 3 s plus 3. How can we get now? K minus 1 is equal to s plus 1 times gs, where s is equal to minus 1. So we will get, what is the function? Here you can see 5s plus 3 divided by s plus 2 times s plus 3, where s is equal to minus 1. Minus 1. So if you write minus 1 replaced by s, you will get what? Minus 2, 1, 2, 2. So it will be minus 1. Let's get k minus 2 is equal to s plus 2 gs, where s is equal to minus 2. It will be 5s3 divided by s plus 1 and s plus 3, for s is equal to minus 2. So for the numerator, you will get minus 7. As you see, in here we will get minus 1. For here, we will get 1. So it will be minus 7 divided by minus 1. It will be 7. What about the last one? K minus 3. S plus 3 times gs, where s is minus 3. You will get 5s divided by s1, s plus 2, where s is equal to minus 3. For the numerator, you will get minus 12. For the denominator, you will get minus 2 and minus 1. So you will get finally minus 6. So we can write this equation now. What is the k minus 1? It's equal to minus 1, okay. 1 over s plus 1. What about the second one? 7 divided by s plus 2 and 6 divided by s plus 3. Now we can convert this equivalent easily to the time domain. How? It will be 8 power of minus t plus 7 8 power of minus 2t minus 6 times 8 power of minus 3t. How can we convert it directly? Of course, I used my experience and also maybe I can show you inverse Laplace table. Yes, as you see here, 1 divided by s plus a is a to power of a times t. Okay, so by using it, we can easily convert this function to the gt into the time domain. Okay, if gs has multiple order poles, what we do now, what does mean? gs is equal to qs divided by s plus s1, s plus s2, and blah blah, s plus se to power of r. Okay, so how can we expand this function? gs is equal to ks1 over s plus s1 plus ks2 divided by s plus s2 and blah blah until multiple order poles. What we have, a1 divided by s plus se plus a2 divided by s plus se square, a3 divided by s plus se whole cube, and blah blah. Now we can write ar divided by s plus se r. Okay, how can we convert now? We know this part. We can get ks1 and ks2 easily, which is learned before. But how can we get a1, a2, a3 and ar? Let's do this now. Okay, ar is equal to s plus se to power of r times gs, where s is equal to minus se. Okay, what about the others? ar minus 1, differentiate with respect to the s, again s plus se to power of r gs, and again of course s is equal to minus se. Okay, what about the other? ar minus 2, 1 over 2 factorial, and the second order differentiation with respect to the s plus se r gs, s is equal to se minus se. Okay, we can find these coefficients as like that. Finally, a1 we can get 1 over r minus 1 factorial d to power of r minus 1 over ds r minus 1 s plus se r gs, again s is equal to minus se. We can find this like that, okay, by using these formulas.